Okay, guys, all the reactions represented above occur in aqueous solution of occur in an aqueous solution of oxalic acid. Which of the following pair represents a Bronsted-Lowry conjugate acid-base pair? This is very basic acid-base theory. I'm pretty sure that one of the 60 questions every test is there. A conjugate acid-base pair have to be identical in all respects except for one hydrogen. So it's not A. They are different by 2 hydrogen. It is B. This has carbon. This doesn't even have carbon. And these, again, differ by 2 hydrogen because this has 3 H plus, this has 1 H plus. And so they have to be identical in all respects, and they have to be in the same equation. You can see right here, a conjugate acid-base pair here would be H2O and H3O plus, but it is B. That's a pretty easy question. Hope you got it. Okay, here's my favorite. Which of the following reactions is not thermodynamically favored at low temperature but becomes favored as the temperature increases? Remember, we talked about the chart. And so delta H negative, delta H positive, delta S negative, delta S positive. Guaranteed you'll get one of these. Negative is spontaneous or favored at low temp. This is spontaneous at high temp. This is never, and this is always. And so which of the following reactions is not thermodynamically favored at low temperature but becomes favored as temperature increases? You're looking for the only choice in which delta S is positive and delta H is positive, and I do believe this is positive and this is positive, and the answer for 12 is B, and I really hope that you didn't miss that because we did a bazillion of those, and I really suck as a teacher if you miss that. Which of the following diagrams, particulate diagrams, best shows the formation of water vapor from hydrogen gas and oxygen gas? Okay, so here's the deal. Hopefully I taught you Brauncliffe. Hydrogen and oxygen are diatomic. So the first thing you got to do is you got to throw out A because it's monatomic and B because it's monatomic. And right now that leaves C and D because they're diatomic. And then the other thing you got to know is H2 plus O2 goes to H2O. And because there's a 2 here and a 1 here, you need 2 here and a 2 here, and the mole ratio tells me that you need to have twice as much hydrogen, and hydrogen is tiny, than oxygen. And so the one that makes, let's just count, over here I got 1, 2, 3, 4, 5, 6 H2s, and 1, 2, 3, 3 O2s. And they go to 1, 2, 3, 4, 5, 6 H2O. That one looks like it's working. This one, 1, 2, 3, 4, 5, 6 H2s, 1, 2, 3, 4, 5, 6 O2s, and then 1, 2, 3, 4, 5, 6. This one doesn't have the right mole ratio. It has to be that one. Okay, we talked about this. Okay, so this, it looks to me like the equivalence point is 40. If you put in more than 40 moles of NaOH, you're going to have an excess of base. If you put in less than 40, you have an excess of acid. S is a very important point. It's called the half equivalence point. And why that's so interesting is when you have a weak acid and a strong base, at the half equivalence point, half of this is gone. So half is gone. Half of the total that's going to be formed is formed. And what's interesting is the ratio of the conjugate acid, the ratio of the conjugate base over the acid is 1, and so that's interesting. A 50 ml sample of HA of unknown molarity is titrated, and the pH of the resulting solution is measured with the pH meter and graphed as a function of the volume of NaOH at point R in the titration. Which of the following species has the highest concentration? And it is HA. It would maybe be this, or it would be a tie, but this is a weak acid, and so you don't get a whole lot of H plus coming off of a weak acid. And the reason why you know it's a weak acid is that the pH is above 7. And so at this point, at point R, you still have, you're not to the halfway point, so R has the most. And then I did 1 per page, and then 15, I put this on every page. What's going on at U? Well, U is on this side, so 20 mils more. So all of the acid is gone. And so you have this weak acid, and then you have sodium hydroxide, and then it turns into some sodium salt and water. And on this side, you have an excess of base, meaning the equivalence point was 40. So you have 20 mils of unreacted base because all of the acid is gone. So you have to pick one. This is gone. You have to pick one that has Na plus, A minus, and then OH minus floating around. No water because it said to other than water. And so the only one that makes sense is not C because C has HA in it, and not D because D has HA in it, and not A because we're 20 mils past the equivalence point, so there has to be some extra OH laying around. So the answer has to be B. Okay, and then next one, I know we talked about these, but just do it again. At which point on the titration curve is the concentration of A minus closest to twice that of HA? I don't really like the way this is worded. It takes me a while to figure out. At which point on the titration curve is the concentration of A minus closest to twice that of HA? And so you have twice as much of this as this, but you still have some of this, so you can't be over here. And the only point that makes sense, in my opinion, is C, because you have to be on this side of the half equivalence point because you have more conjugate base than acid, but you still have some acid around, so you have to be in this region. You have to be on the half equivalence point, but not to the equivalence point. And I'll just check 15, no, that's 16. Yeah, 16. The answer is C, point T, and I think I got it right. Okay, and then 17. Oh my gosh, did I screw this up in class in first hour? So here's the deal. Remember I showed you this MA VA equals MB VB, and let me say it again, this only works if you have 1 to 1 to 1 to 1. And the problem told us, I kept copying it down, you have and so the question is, what is the molarity of the acid? Well, the molarity of the acid using 9th grade algebra is the molarity of the base times the volume of the base over the volume of the acid. If you look at the chart, or if you look at the problem, I told you the molarity of the base was 0.1. And the volume of the base at the equivalence point comes off the graph. It's 40. And the volume of the acid is right here, a 50 milliliter sample of acid. So the volume of the acid is 50. And so now this is the crazy part. What is 40 over 50 is 4/5. So I'm going to take 4/5 of 1. So it has to be one of these two answers. Now, here's why you got to understand the slightly more, slightly less. When you do an endpoint with color, you have to overshoot the endpoint because just by a couple drops to get up, like phenolphthalein doesn't turn purple till it's above 9. And so what happens is you actually get a little bit more than the equivalence point. So this volume might not be 40 mils, it might be something like 40.2 mils because you have to overshoot the equivalence point to get to the endpoint to get the color change. But because it's that slope of that tangent line is so incredibly steep that you only have to go 2 or 3 drops. But what you understand about error analysis is this number is a little bit bigger than it should be. And so you won't get exactly 0.08. You'll get B, slightly more than 0.08, because this number is bigger than it should be, and it's in the numerator, and it makes the answer bigger than it should be. And so the answer for 17 is, holy mackerel. Oh no, that's 16. What's going on? I don't know what I'm doing. I got the wrong answer. Yeah, the answer is B. All right. Okay, this one, refer to the three gases in identical rigid containers under the conditions given in the table below. Okay, so we got the name of the gas, we have the weight of the gas, we have the molar mass. So this is the lightest gas. We have the temperature, and we have the pressure. Interesting. Okay. Average kinetic energy of the gas molecules is D, the same in all containers. Why? Remember this curve? I'm sorry. Yeah. If you have gases at the same temperature, oh, I can't say that. Refer to the identical. I mean, oh, need to be careful. No, I'm okay here, I think, because if they have the same temperature, they have the same kinetic energy. So the answer is D. I was looking at the pressure. I think it's I always say same temp and pressure, but I think they only have to be the same. D, this option is correct. The average kinetic energy is a function only of the temperature, and each vessel has the same temperature. So 18, the answer is D. 19, the density of the gas is, now remember, density is mass over volume. And so I would not say the density is the same, because they are interesting. So this one, because it has the biggest mass, I think it's the most dense, but this is bugging me here. I gotta think about how I did this problem. B, why is it the biggest in B? This option is correct. Since all three containers are at the same temperature, the number of particles per unit volume is directly proportional to the pressure. The density is mass per unit volume, so the density is proportional to the product of the pressure and the molar mass. This product is greatest for container B. Oh, that's awful. How would I do this? I would do this. Mr. T conquers over pervs. And then remember that mass over volume is density. And so Dr. T conquers over pimples, let's say. I said think of a dermatologist. And then solving this quickly, just so this makes sense, taking cross products, you get Dr. T equals molecular mass times pressure, or the density of all these gases is molecular mass times pressure over RT. And R is the same and T is the same. So what the answer key is saying is that the density is proportional, because these are the same, to the molar mass times the pressure. And so if you do this, molar mass times the pressure, this would be 32. 30 times 4 is 120. Remember, I don't have a calculator. And 58 times 2, 16 carry the 1, this is 106. And so if you understand this formula, because R is a constant and all of the temperatures are 300 K, and so density, you can tell the one that's the most dense by which one has the greater product of molar mass times pressure, and that is gas B. That's a tougher problem than I thought it was. If the pressure of a gas is increased at constant temperature and condensation occurs, which gas will condense at the lowest pressure? And the question is, remember now, phase changes like condensation are related to intermolecular forces. So phase changes are related to intermolecular forces. Now, all of these are nonpolar molecules, but this one has the weakest dispersion forces because it has the fewest electrons. So these have the weakest dispersion forces. These have the strongest dispersion forces, because more electrons is more polarizable. Remember now, polarizability just means by chance the electrons are moving around the nucleus at the speed of light, and sometimes there's more on one side than the other. And so when I'm looking at this, the intermolecular forces of butane are the strongest. And when things have strong intermolecular forces, they're attracted to each other and they condense. And so the lowest pressure, meaning which one will condense the easiest, you have to have the lowest pressure on it. I believe that's butane because it has the strongest dispersion forces. And that is the answer. And so when you, one of the things you do to get stuff to condense when you have gases is you increase the pressure and it pushes the molecules closer and closer together, and they can't overcome those intermolecular forces and they condense to become a liquid. And so remember, phase changes are related to intermolecular forces. Okay, this is a crazy problem, but I'm going to stop. I'm coming back to this one because I said I would do 10 at a time.